Clearing the confusion. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we are going to tackle two of the most common points of confusion about elliptic curve cryptography: its relationship with hashing, and how it is actually used for encryption and decryption. Many people are surprised to learn that ECC is not a hash function, and that you do not directly encrypt data with it. In this presentation, we will clear up these misconceptions and give you a precise understanding of ECC's true role in modern security. Recap: what ECC actually provides. Before we discuss what ECC isn't, let's quickly recap what it is. ECC is a type of asymmetric cryptography. This means it operates using a key pair: a public key that can be shared with everyone, and a private key that must be kept secret. From this foundation, ECC provides us with two powerful tools, or primitives. First, key exchange, through the ECDH protocol, which allows two parties to establish a shared secret. And second, digital signatures, through the ECDSA protocol, which allows someone to prove their identity and the integrity of a message. These two tools are the building blocks we use to construct secure systems. ECC and hashing. Let's address the first point of confusion: hashing. The most important thing to understand is that ECC is not a hash function. They are completely different types of cryptographic tools with different goals. A hash function's job is to create a unique, fixed-size fingerprint of data. ECC's job is to perform operations related to public and private keys. However, while they are different, they work together. ECC uses hash functions as a critical component in its operations, especially for digital signatures. What is a hash function? Let's quickly define a hash function, like SHA-256. Its job is to take an input of any size, from a single word to a multi-gigabyte file, and produce a short, fixed-length string of characters. This output, the hash, is a unique fingerprint of the input data. A good hash function has three key properties. First, it's deterministic, meaning the same input always produces the same output. Second, it's a one-way function, meaning you can't figure out the input from the output. And third, it's collision-resistant, meaning it's practically impossible to find two different inputs that produce the same output. Where ECC uses hashing: digital signatures. So, where do these two technologies meet? The primary intersection is in the elliptic curve digital signature algorithm, or ECDSA. When you sign a message, you do not actually sign the message itself, as that would be very slow and inefficient for large messages. Instead, you first create a short, fixed-size hash of the message using a function like SHA-256. Then, you use your ECC private key to sign the hash. The relationship is one of composition. ECDSA is the signing algorithm, and the hash function is a tool it uses to prepare the data for signing. The ECDSA signing flow. This diagram shows the flow. The original message, which could be very large, is first passed through a hash function like SHA-256. The output is a small, 32-byte hash. This hash is what gets fed into the ECDSA signing algorithm, along with your private key. The result is the digital signature. By signing the hash instead of the full message, we gain a massive performance advantage and create a signature that is a standard, predictable size, regardless of the size of the original message. ECC and encryption. Now, let's discuss the second major point of confusion: encryption. While it is technically possible to directly encrypt a small amount of data using some ECC schemes, in the real world, you do not use ECC to directly encrypt large messages. The reason is simple: asymmetric cryptography is extremely slow. It involves complex mathematical operations that are orders of magnitude more computationally expensive than the operations used in symmetric ciphers like AES. Using ECC to encrypt a large file would be painfully, prohibitively slow. The armored truck versus delivery van analogy. Here's a good analogy. Think of asymmetric cryptography like ECC as an armored truck. It's incredibly secure but very slow, expensive, and can only carry a small, high-value item. Think of symmetric cryptography like AES as a fast delivery van. It's extremely fast and efficient and can carry huge amounts of cargo. You would never use an armored truck to deliver a city's worth of packages. It's just the wrong tool for the job. The smart approach is to use both tools for what they're best at. The solution: hybrid encryption. The solution is to use a hybrid encryption scheme. This approach combines the strengths of both asymmetric and symmetric cryptography. We use the slow, powerful armored truck, or ECC, to securely deliver one tiny, precious item, the key to the delivery van. Once both parties have this key, they use the fast, efficient delivery van, a symmetric cipher like AES, to encrypt and transport all the actual data. This gives us the best of both worlds: the secure key establishment of asymmetric crypto and the high-speed performance of symmetric crypto. ECDSA, the hybrid encryption standard. The standard way of doing this with elliptic curves is called the Elliptic Curve Integrated Encryption Scheme, or ECDSA. This is not a single algorithm, but rather a full recipe that combines several cryptographic primitives to achieve our goal. It uses ECDH, elliptic curve Diffie-Hellman, for the key exchange, a key derivation function, KDF, to generate the symmetric keys, a symmetric cipher like AES for the actual encryption, and AMAC function like HMAC for ensuring integrity. Let us walk through how it works. ECDSA encryption. The setup. Let's set the stage. Alice wants to send an encrypted message to Bob. Bob has a long-term ECC key pair, his private key DB, which he keeps secret, and his public key QB, which he has shared with Alice. Alice has the message she wants to send, meet at midnight, and she has Bob's public key QB. ECDSA encryption. Step 1: the ephemeral key. The first thing Alice does is generate a brand new, temporary ECC key pair just for this one message. We'll call her ephemeral private key DE and her ephemeral public key QE. This is a crucial step. By using a temporary key, she ensures that each message is cryptographically independent, which provides properties similar to forward secrecy. ECDSA encryption. Step 2: the shared secret. Now, Alice performs an ECDH key exchange. She takes her ephemeral private key, D_E, and Bob's long-term public key, Q_B, and multiplies them together to compute a shared secret point, S. Because of the properties of Diffie-Hellman, we know that Bob will later be able to compute this same secret point using his private key and Alice's ephemeral public key. This shared secret is the foundation for the encryption keys. ECDSA encryption. Step 3: key derivation. The shared secret S is a point on the curve, not a key that's ready to be used. So, Alice passes the x-coordinate of S through a key derivation function, or KDF. The KDF is a cryptographic algorithm that stretches and splits the secret into two new, independent symmetric keys. A key for encryption, let's call it K-Enc, and a key for authentication, let's call it K-Mac. Encrypt and MAC. Now Alice has the keys for her delivery van. She uses the encryption key, KENC, with a fast symmetric cipher like AES to encrypt her plaintext message. The result is the ciphertext. Then, to ensure integrity, she uses the authentication key, KMAC, with a function like HMAC to create a message authentication code, or tag, of the ciphertext. This tag will prove that the message hasn't been tampered with. ECDSA encryption. Step 5. The final package. Alice is now ready to send her message. She assembles a final package containing three things. First, her ephemeral public key, QE, so Bob can compute the shared secret. Second, the ciphertext of the message. And third, the message authentication code, or MAC, she sends this entire package to Bob. Notice that her ephemeral private key and the symmetric keys were never transmitted. ECDSA decryption. Recreating the keys. When Bob receives the package, he reverses the process. He takes his own long-term private key, D_B, and Alice's ephemeral public key, Q_E, which she sent him. He multiplies them together to compute the shared secret point, S, since D_B times Q_E is the same as D_B times the quantity of D_E times G, and Alice had computed D_E times the quantity of D_B times G. They both arrive at the same secret point. Bob then passes this point's x coordinate through the same KDF to retrieve the exact same K_ENC and K_MAC that Alice generated. ECDSA decryption. Verify then decrypt. Now that Bob has the symmetric keys, he performs the final steps. First, and this is very important, he uses the K_MAC key to calculate his own MAC of the ciphertext he received. He compares his calculated MAC with the MAC Alice sent. If they don't match, he knows the message has been tampered with and he discards it immediately. If they do match, he knows the message is authentic. Only then does he proceed to use the KENC key with AES to decrypt the ciphertext and recover the original plaintext message. Conclusion. Putting it all together. So let's summarize and directly answer our initial questions. First, what is ECC's application in hashing? ECC is not a hash function, but it uses hash functions as a building block for digital signatures. Second, what is ECC's application in encryption? ECC is not used to encrypt data directly. Instead, it is used in a hybrid encryption scheme like ECDSA, where its key exchange primitive, ECDH, is used to securely establish a shared secret, which is then used to generate keys for a fast symmetric cipher that does the actual encryption. ECC is the armored truck for the key, not the delivery van for the data. Final thoughts. Understanding the proper roles of different cryptographic tools is the key to building secure systems. Hash functions create fingerprints, symmetric ciphers do the heavy lifting of encryption, and asymmetric ciphers like ECC manage the keys and identities. By using each tool for its intended purpose and combining them in standardized, well-vetted schemes like ECDSA, we can build systems that are both incredibly secure and highly performant. Thank you for your attendance. Please consider subscribing to the channel.